The lesson today is about differentiation using the power rule. By the end of the lesson, you should be able to prove the differentiation formula by first principles and differentiate simple power functions using appropriate derivative notation. Now, last lesson I introduced differentiation by first principle and the idea of small change, delta y over delta x. And the differentiation written in the Leibniz notation, dy dx is equals to limit of h approach 0, the function of x plus h, take away function of x over h, where h is actually the small change. We find the average rate of change between 2 points, and we keep on moving one point to the other until they're so close that the change is really small. So now, note that if you're given y equals to something, then the notation of the differentiation is dy over dx. Or if you're given fx, then the notation for the derivation is f dash x equals to whatever. Alright, what I would like you to do is to think about the three examples that I showed you yesterday. You got first fx equals to x squared, and then the derivative that I've shown you is f dash x equals to 2x. Then you actually have to work out example 2 and example 3 yourself by first principles. Now, can you actually do a generalization? The generalization, we call it the power rule. Alright? So for any function that can be written in the form fx equals x to the power of n, for example, this is x squared, this is x squared plus 3, x plus 1, and this is x to the power of minus 1. Right? What we can say is f dash x, or the derivative of fx, equals to n times x to the power of n minus 1. So it's pretty much from here you can see. We take the n, it becomes the coefficient of x, and then n minus 1, which is therefore 2x. Same with here, this example 2. So 3x to the power of 2 plus 1x to the power of 0. Alright, this one will be minus x to the power of minus 1 minus 1 minus 1, which is therefore minus x to the power of minus 2, which is written as minus 1 over x squared. Now, let me derive this generalization for you. So let's prove if fx equals to x to the power of n, then f dash x, or the derivative of fx, is nx to the power of n minus 1. So writing it in the limit notation, we know that f dash x is equal to limit of h approach 0, f x plus n minus f of x divided by h. So we now know x plus h to the power of n minus x to the power of n over h. That is the notation that we need to use, substituting into the function x to the power of n. So expanding it, we use binomial expansion. You should know how to do that, and we get the following expression. Then what we need to do is be able to cancel that and rewrite it and eliminate all the h's, and minus 1, and we therefore have limit of this expression, n choose 1, x to the power of n minus 1, n choose 2, x to the power of minus 2 times h, and so on and so forth until we have h to the power of n minus 1. Now we know as h approached 0, what happened? Everything here will become 0, and therefore what is left is n choose 1, x to the power of n minus 1. And you know that in terms of binomial expansion, n choose 1 means n. So it's nx to the power of n minus 1. So therefore, we can derive f dash x is actually nx to the power of n minus 1. Alright. So let's think about the gradient function of a polynomial. It is always a polynomial of 1 degree less. Alright? It is, remember that it's always a polynomial of 1 degree less. So if it is linear, then the degree of fx will be 0 because it is a constant. Quadratic, the degree of fx will be 1, and cubic, the degree of fx will be quadratic. Alright? So therefore, if it is n, the degree of f dash x will be n minus 1. Let's see if you can do some of this example. Alright, if I know y equals to x to the power of 6, dy dx will then be 6x to the power of 5. So I would like you to pause the video for 5 minutes and work out the next 5 examples. Here, f dash x will be 11x, 11 minus 1, which is 10. Now this one will be dx dt, will then be 12t to the power of 2. S as a function of t, the derivative will be f. S of f s dash t will be 3t to the power of 1, which is 3t. And then here, what is 9 pi? 9 pi is actually a constant. Pi is 3.14, so this is actually a number. So therefore, the derivative dy let's say plus 0x, x will then be 0. And then finally for the last one, derivative of function x will be 32 over 5 x to the power of 7 plus 0, because k is a constant, therefore it's 0. Alright, now second last slide. What is the derivative of a constant? Why is the derivative of a constant equal to 0? You know that the derivative is actually the gradient. Since it is a constant, fx equals to k, this is k, and the gradient is therefore equals to 0. Alright? Now this is the end of the lesson. So just quickly reflecting on your learning, hopefully you will be able to prove the differentiation formula by first principles and be able to differentiate simple power functions using appropriate derivative notation.